Next up, we have Meta, and they're going to talk about using simulation to optimize new hyperscale data centers and designs for rack delivery window. Please welcome Mohammed Shariat Madarik, Marcin Starczyk, Peter Lopez, and Lakhwinder Singh.
All right, looks like we have everyone. Mohammed, would you like to bring up the slides?
Sure. Do you see it?
There you go, perfect. Hello everyone, and welcome and thank you for joining us on our presentation, Workflow Simulation in Hyperscale Data Centers. Before we go into the details, just like to give the team an opportunity to introduce themselves. So my name is Peter Lopez. I am a process improvement engineer with Meta. I've been with Meta for a little over 4 years now. I've been working in production operations for about 20. Super excited to share this content with you. And I will hand it over to Lakhwinder to introduce himself.
Thank you, Peter. My name is Lakhwinder Singh, and I'm a data science manager. Have been with Meta for almost the same time as Peter. We joined the same time. In the current role, I am responsible for supporting analytics for 3 core pillars in infra data centers. And I'm also a colleague of Mohammed, so I'll pass it to Mohammed.
Okay. Thank you, Lak. Yeah, my name is Mohammed, and I'm a data scientist in Meta. I'm working at Meta for 2 years, and I help Lakhwinder for doing lots of analytics and data analysis. So I hand it over to Marcin.
Thank you, Mohammed. My name is Marcin Starczyk, and I'm the data center capacity engineer in Meta. I have been with Meta for the last 3 years, and previously, for 15 years, I had different roles in the telecommunication industry. And that's all of us. I'll pass to Peter for the presentation.
Thank you so much, Marcin. All right, so for the rest of the presentation, Mohammed and I will go through details. Marcin and Lakhwinder will join us when we get into Q&A. So we can go to the next slide. So just wanted to cover a quick overview before we go into the details. So I'll talk a little bit about hyperscale data centers and what problem we were trying to solve, and then talk a little bit about rack workflows. There's 3 main types. We'll focus on one in particular for this particular use case. And then I'll show some 3D visualizations to get us started on the modeling approach. And then at that point, I'll hand it over to Mohammed, and he'll talk about some of the details of the model itself, the assumptions, the parameters. He'll show some of the results with you and go through the optimization, and then close with Monte Carlo simulation and next steps. So what is a hyperscale data center? The less exciting answer is that it's a really big, massive building. So think multiple football, soccer field sized buildings. And you could see an example of a site that we have there in the upper left-hand corner. So these are examples of our H design. And then right next to that on this particular site is an I design. So the campuses are fairly large in nature. The more exciting answer about hyperscale data centers is that they're filled with thousands of servers and racks and network equipment. And all of this, connects family and friends through one click on the phone, or connects us in the metaverse when we put on our VR glasses. And all the teams that support the workflows that we're going to talk about here, they're highly skilled resources. And so we want to optimize the workflows, how we stage that work, how we plan for that work. That is really, really important to us. So the cost, the high availability, and how we do that with partnering with our teams is super important. So in the upper right-hand corner, you can see an example of Emilio. This is one of our technicians in the data itself, and he's working on the servers on a particular rack within the data center. So this provides a little bit of context around what the overall building looks like and then what's in the buildings. So what we've done is we've modeled different design aspects of these workflows. So think workforce availability, the designs of the data centers themselves, the throughput that's needed in order to do the things that we need to do to provide the capacity and the availability. And we're leveraging the AnyLogic software to validate this. So how do we optimize? How do we come up with the best solutions? How do we plan in the future? All those types of things. So that's just a quick overview, and happy to answer any more questions as we get into more details of the presentation and answer them at the end. All right, so what are the 3 types of workflows that are available to our racks? The first one is receiving. In this case, what's happening is a data center is coming online. And so we're bringing racks into that particular data center and essentially turning it up and ramping it up. And then the second one is redistributing those racks. So if we need to move racks around for resiliency, or we need to make space available for a very specific type of rack, then we might go through this workflow called redistributing. And then the last one is refreshing. So let's say that the hardware is getting older, we need to refresh that hardware, or we need to do a complete retrofit in a space. Then we would go through this workflow called refreshing, where we would actually move them out of the building itself. Each of these different workflows have multiple steps, and Mohammed will talk about those steps as he goes to the details of the model. Kind of the opportunity here was that we didn't have a really good process and a tool to visualize and simulate the operational constraints in these different data designs and with the teams to understand bottlenecks and throughput capability. So we're going to share with you kind of what our approach was to get into a better space. All right, in the next slide. So we're going to kick off the model approach. So the very first step is visualization. So what this is an example of, and Marcin developed this for us, we can pull in a site layout. So this is an example of a general design for a data center. And what you can see is the trucks actually coming to us from the integrator, coming into the receiving area. So they're being unloaded from the truck. At that point, we do some quality checks, we verify them, and now they're moving actually into the space within the data center itself. And so we can actually see the entire workflow in the space where it's going to happen. And we're doing this way far in advance. So we do this prior to construction. We can have really robust conversations with our cross-functional teams around, are there issues within the flow? Are there considerations that we should be thinking about that weren't obvious before we started this process? So it creates a really robust and insightful conversation with all of our cross-functional teams around the best way to approach the workflows that we're going to go through here with you today. So that becomes the very first step in our modeling approach. So that's our agent-based visualization. That gives us insights into discrete event simulation and setting up the parameters for how we would set up these models. And then we can optimize those and really just go through an iterative process there, and then build confidence in the model through the Monte Carlo simulation. So with that, I will hand it over to Mohammed to go into the details of the model from here.
Thank you, Peter. Hello again. So I'll continue the presentation till end. So after agent-based visualization, we need to create a discrete event simulation. So for having a discrete event simulation, we need to have some assumptions. So the first assumptions that we assume is the hyper data center is an object with multiple parameters in the AnyLogic platform. And also we wanted to predict throughput of the variety of hyper data centers. And for the process that we want to model is rack receiving. The rack receiving process has multiple steps. We have receiving and positioning that is related to team 1. Then we have energizing is related to team 2, and cabling team 3. And for provisioning, it's automated. The other assumption is we assume that the simulation is just for 1 week, and the throughput numbers is not just absolute number, there are just percentage. And the number of resources in each team is configurable, and we we set the utilization between 60% and 80% for each team. And we assume that the shift starts at 8 a.m. by default, and overtime is allowed. The team one processes includes unloading the truck, unpacking and paperwork. We have some dock queue, and we need to run from dock to data halls. And we need to go to, if you go to the second floor, we need to use elevator. And going to first or second floor is by the chance in this model by 50-50%, but we can change it by by decision. And for energizing and cabling, we assume that there are no normal distribution. In provisioning, we have two steps: switch provisioning and server provisioning, that are set to 80%. It means that 20% of the time we need to do rework. One of the good features in AnyLogic is we can create UI for our model, and we can change the parameters and see the results. And we did the same thing, and we created a very good UI for our model, and each user can change the parameters. For example, team one, we have three kinds of people: unloading, unwrapper, and tagging, or mover people. So you can change the number of people, and a start time you can change. And if you need to add overtime, you can add overtime to the that team. And also we have lots of other parameters. For example, if you want to change the unloading time for each rack, we can just change the number here for the mean and max. And in the model, we assume that it's a uniform distribution. Similarly, for team 2 and team 3, we have these kind of parameters: number of people, and the start time and overtime. Just for energizing and cabling, we assume that there are normal distribution, and we need to add the mean and standard deviation for each building. And for provisioning, we set them to 80%. It means that 20% of the time they need rework. And this is the discrete event flowchart in AnyLogic. You can see it starts with receiving. It's very straightforward, and then it goes to paperwork and unloading truck and removing packages. And if we want to go to first floor, we need to just move the racks to data hall and get back. And if you want to go to second floor, we need to go to elevator and use elevator and go up and move racks to data halls and getting back to dock. After that, team 1, team 2 starts energizing the racks, and then cabling starts with team 3. And after cabling, provisioning starts. As you can see, we have 3 kind of resource pools here for each team. If we run this discrete event simulation with regular values, regular parameters, the regular parameters are like this. Team 1, we assume that we have 1 unloader, 2 unwrappers, and 6 movers. For team 2 and 3, we assume that we have 10 people. And a start time for each team is at 8 a.m. And overtime is not, we don't have any overtime. If we run the model, we can get 40% of throughput, but the target is 100%. And the average duration by days is 3.7. It means that from unloading racks till putting in use the racks, that we can use it for our applications and for other stuff, it takes 3.7 days. And this table shows the funnel it means that after 100% receiving, we just could complete 60% of the racks put in their positions. And we could complete energizing, but for cabling, we just could complete 40% of those racks. And provisioning was completed as well. So it means that cabling and in positioning are two bottlenecks in our process. This chart shows the bottlenecks clearly: unloading and cabling. So for solving these issues, we know that the bottlenecks. So we need to find out the optimized value for each parameters. So we decided to have an optimization model for this simulation model, and the objective function is maximizing the throughput. And the constraint that we have is throughput cannot be more than 100%, and the number of people for each team is less than 20, and a starting time is varying between 8 a.m. to 10 a.m. for each team, and overtime is between 0 to 2 hours, and utilization is set to between 60% and 80%. We ran this optimization model for 2,000 times, and we got these results. The result shows that for team 1, we need to have one unloader and 3 unwrappers and 6 movers. It's good to start at 8 a.m. for team 1 without any overtime. For team 2, we need 19 people, and it's better they start at 9 a.m. with 2 hours overtime. And for team 3, we have 20 people. They better start at 10 a.m. and 2 hours overtime. If we run that, based on this optimization, we could get 92% throughput. And this chart shows the result of optimization. We have some infeasible results, but we are just looking for the feasible results. If we run the model again based on the optimized values, as I said, we can get 92% throughput, but the average duration is 2.2. It means that we decreased 1.5 days. The previous model was 3.7. And it's very good for us. We can have more racks in 1 week. And this chart shows that we don't have any bottlenecks. Just provisioning, we just could complete 92%. And this because of the simulation timing is just for 1 week. It's not, if we add more hours, it can complete it, because this provisioning is automated process without any human interference. Okay, so by having an optimized model, it's not good to just share the results to stakeholders or your managers that the model throughput is going to be 92%, because we need to have, in real world, we have lots of uncertainty and a stochastic process. So it's not safe to just share the results from optimized model. So for solving that problem, we need to use Monte Carlo method. Monte Carlo, if you are not familiar with that, is a stochastic method that uses a random sample of inputs and creates an output for the model. If we run the Monte Carlo method multiple times, we can get a distribution of output. And instead of having just one scenario, we can have multiple scenarios at the end. And in this chart, you can see we have a random sample of inputs for the model, and we feed it to the model, and we run it 10,000 times, for example, and we can get a distribution of output. and we can do lots of statistical analysis, data analysis on the output. So I have two charts here, just focus on the blue one. So this is the result of the Monte Carlo simulation for optimized model. We ran the model 10,000 times, and we got this result. It's the x-axis is throughput, and the y-axis is the probability of that. This blue chart shows that the 40% of the time we got the results, the throughput is going to be 90%. But we still have some other options as well. For example, 3%, 30% throughput is having a 20% chance. So it's not safe to say that the model is just having 90% output. But it's more, the most probable outcome for the model because it's the mode. So the mean of the model is 62%. Yes. So for the next steps, we want to add redistributing and refreshing that Peter explained at the beginning of the presentation. And also we wanted to add energizing, more steps and details for energizing and cabling and provisioning. And also adding sensitivity analysis to the model is a good thing, and we can just understand the best values for the parameters. And after adding these steps to these features to the model, we can increase the time of the simulation to 1 year or more to do more analysis. Yeah, that's it. I'll pass it to Q&A.
All right, it looks like we have some questions that are in the queue. So there was a question, do you think your model will work to different scenarios, like avoiding some of the constraints? So I think maybe I could take a first cut at this one. I think one of the powers of having this model is clearly identifying where the constraint is. And if we think about a theory of constraints approach, we want to exploit those constraints once we understand them. So we would definitely work to make that portion of the workflow more efficient. Like maybe we could do work in parallel. Maybe we could think about how we would be more efficient with our tooling and those types of things. And then to Mohammed's point around how we would evolve the model, once we understand that, then we can actually build that into the new baseline of what the model looks like to identify maybe where the next constraint is, and then kind of go through that same process. So to me, it's not avoiding them altogether, it's understanding where they are. And then once we understand where they are, then we can work to improve that part of the process. That's the most critical piece. That's what's going to move us faster to be more efficient and more thoughtful with our resources. So I don't know if there's anyone else on the team that would like to talk to that as well.
I can add to it, Peter. I guess we have added like bunch of constraints. I mean, which we feel like which we need when we are doing the operations. We can run the model based on some constraint, and we can tailor the model basically based on like whatever constraints we need. We think like will be responsible.
Mm-hmm.
And it also depends on like different types of environments we might be running. I mean, we have various types, so the model also takes care of that. I hope like this answers the question.
Mm-hmm. Mm-hmm. Maybe we could jump to the next one. So the next question is, why do you set the simulation to 1 week?
Maybe I'll take this one. So, I mean, because usually we work on the deliveries on the weekly basis. However, this is configurable, so we can change the length of the simulation. It was just easier to present to X7 partners because we just work on a weekly time period.
Yeah, that's perfect, Marcin. I think the other thing too, like Mohammed alluded to this, like we want to understand different timeframes. So like a weekly consumption is good for the people that we work with, right? Our teams can resonate with that. But we also look at daily, we can look at shiftly, we could look at long time horizons. Like that's one of the great things is we can configure this to look at it in different ways. But to your point, the whole idea around building the model is we want to be able to socialize that with people that can use it. And so we want to build it in a way that it's consumable and usable by our customers. But typically, you're right. Like we look at throughput from a weekly perspective. All right. Maybe one of you guys wants to jump into some of these other questions. They're coming in all over the place. So.
Yeah, I think I can take the next question. How do you solve the problem of correlation among exposure variables? So this is the simulation that we run, like the processes are exhaustive processes. Like they're not dependent on, they are dependent on each other, but they are independently performed by like separate teams. There will be, it's a great question. We have not looked into correlation yet, but maybe in some time in the future, we'll probably look. But at this moment, intuitively, they are exhaustive processes. So we feel that correlation will be minimal there. Hope this answers. And anybody want to add anything on that?
Makes sense. Okay, I'll take the next one maybe. There is the question, is there a connection between the agent-based visualization and the discrete event simulation? So in fairness, there is not. We used on purpose the agent-based model for mainly for verification, not for validation and not for getting the numeric data. And the reason for this is that even though the objects, they give the flexibility, for moving racks or lifts, for example, there is a lot of flexibility there. But at the same time, if the object doesn't have the parameter we want to change, it's difficult or it's time consuming to add it. So basically, no. I mean, the answer is we have not merged it yet. We use the visual one or agent base for verification, and then numerical values are coming from the ES model. It's easier to modify. And then on the second note, so like do you use, I'll just answer this one because it's the similar stuff. Do you create a different simulation model from scratch for each new DC? So no, we did like kind of template it, especially for the agent-based one, because it's something which you can like create the layers and then just change basically the blueprint and the layout of the DC. So this is standardized.
Mm-hmm.
Cool. I guess I can also give a perspective on this agent versus discrete event simulation. Agent-based is basically, as Peter shared before, like if you think about data centers, these are 4 times the size of the soccer field, like just one building. Getting all of that at one place, so that agent-based simulation gives us that. Discrete event simulation gives us like power to run different scenarios, like we can alter different operational constraints and get to the operational output that various stakeholders across within internal teams within Meta would like to benefit from, because these are unseen scenarios that we have not run until now. So we get like some educated guesses and make some data-driven decisions around them. So that will be my take on that.
Thank you, Lakwinder. All right, I think we're getting pretty close on time, so maybe we have answer for one more. Mohammed, did you have one on the list?
Yeah, I think one question is related to Monte Carlo simulation. The results with the Monte Carlo optimization are much more lower compared with your first results. Yeah, so as I explained, the first model that we ran, it was just one output. It wasn't the distribution, and it didn't calculate the uncertainty and stochastic of the inputs. So if we run it multiple times, it says that just 92%, we have just 40% of the time we can get 90%. But other times we have other throughputs. So in real world, it makes sense because sometimes we have some disaster, or sometimes we don't have enough people for moving racks around. So it's totally makes sense to have lower numbers in Monte Carlo.
Thanks, Mohammed. I think we're at time, so maybe we could just say thank you to everyone that joined us for the presentation and taking the time to ask us some questions. Thanks so much, John.
Thank you.
All right. Well, thank you guys so much. Thank you, the Meta team.